Alright, so for my math project, I did math project 8, and for the first part, it said carefully graph f of x equals x cubed minus 3x squared. And you're supposed to find the critical points. So I plugged that into my graphing calculator, and I came up with the cubic formula that looks like, the graph that looks like this. And then to find critical points, I found the derivative, I set it equal to 0, and I got 0 and 2. Then for the inflection points, I did the second derivative of f, and then I found 1 for an inflection point. The second question asked me I define the local minimums and the local maximums. So to find those, you, with the critical points that you found, you plug back into your original f equation, and I got -4, and then I got 0. And then when I plugged it back into my second derivative equation, I figured out that I have mins and maxes at 2 and 0. So my minimum is at 2, and so it's going to be like, my minimum is going to be down here at 2, and then my maximum is going to be at 0, because that's like the parabolic curve looks like that. And then after I found my mins and max, it says that you have to find the integral between f of x and the line that goes through your critical points. So after I drew the line through my critical points, I found the equation of that line, that linear line as well. So I did this point slope formula, y2 minus y1 over x2 minus x1. So I found that my slope was going to be -2. I plugged it back in with the points, the -2 and the 2 and the -4, and I found that my B answer was going to be 0. So then the equation of the line equals y minus 2x plus 0. So then I can finally find the integral of it. So when I evaluated the integral between b and a, and from f of x minus L of x, the equation I just found. So I evaluated from b and a in my formula from before, that was my x values, which were 2 and 0. So I plug those into my equation. I take the integral of x to the third minus 3x squared minus a minus 2x, because that was the equation of the line we just found. And then after that, I found the integral, and I plugged in 0, 2, and the area which is the integral, is equal to -8. So, and then it said, number 3, the third part of it, said to make up your own, cubic formula. So then I made up g of x equals x cubed minus 6x squared. I took the derivative of that to find my critical points, which equaled 0 and 4. And then I found my inflection points, which, just like I did before. And then I found that my minimum is going to be -32, and I have a maximum at 0. So my graph pretty much looks the same, except for the p-value is down lower, and my scale goes by 5 instead this time. So then again, I had to find the equation of the line that passes through these new inflection points of the new graph that I made. So I found out after doing point slope formula again, I found my slope, I plugged it back in, I plugged in y, -32 for y, and then 4 for x, and I found out that my new line slope is the formula for the new slope is y equals -8x. And then once again, I could find the integral for the new formula, which is going to be 0 and 4, because those are my x values in the q and p points that I had before. So I took the integral of that again, and then I plugged in 4, because 0 I don't have to plug in, and then my answer was -64. Even though your area cannot be negative, I found, well, this is for the next part, that my pattern was that the original equation given, x cubed minus 3x, is a cubic equation with a minimum and maximum. I made the equation that passes through the min and max, y equals 2x plus 0, and then I solved the integral between a and b. What I found, that was my area was 8, and then when I did it again, when I made up my own equation, the area doubled. So I believe that the pattern, every time you do, it's going to be like 8, 64, and then it's going to keep on going, and then it's going to be like -512. So 8 to the first power, 8 to the second power, 8 to the third power, and then it'll just continuously grow at that grade exponentially, because I feel like that's the pattern that I found in my equation. So then for the next part, number 4, they are supposed to find the area between Q and R. And R is the point where the linear line meets with the cubic function and it intersects. So first I had to find the intersecting point and what the R values, X and Y values were. So then I took the equation of my cubic function and I set it equal to my linear function, and I found that the once I've set that equal, I can find my x value, and my x value is going to be 1. So then I plugged it back in my equation, and then I found the y value to be -2. So r equaled 1, -2, which matched up with my graph perfectly. So after I found the equation of my line, I was supposed to find the area between Q and R, and then I was supposed to find the area between R and P, and I was supposed to like compare them together. So I integrated the separate parts. So first I did from 0 to 1. So then the Q point is going to be like, it starts at the origin, so the x equals 0, and then the x value of R is equal to 1. So 0 to 1, I did the same formula as before, f of x minus L of x. So again, I already have this derivative solved out, so then I just plugged in the 1, and then when I plugged in 1, my area the area between 0 and R is going to be 1. So then I looked for between the area of R and P so I could compare them. I had 1 and 2, and then I plugged in both those numbers. So I plugged them in, and then I found out I got -1. And since your area can't be negative, they're both equal to 1. So I found that both the areas are equal to 1 since the area cannot be negative, and the area of QR is equal to the area of RP, which also is like kind of like a prequel to the idea that they're symmetric in shape. So then for number 5, I was supposed to translate the axis in such a way that the new origin is at the point R, and then I was supposed to find the new equation of that. So I plotted the same cubic function I did before, and I found that if I wanted to bring the origin of Q back down to R, so the new origin was going to be at R, that I needed to translate y needed to move down 2 values, and x needed to move to the right 1. So the new equation of the line would be, you just have your x values and be x minus 1, because you want it to move to the right, and then minus 3 times x minus 1 to the squared, and then y minus 2, because you want it to move down 2. So then my new origin was at the point R. So then every single point, therefore, so like the P moved down 2 values and over 1. So it had the same symmetry even though the origin was moved down 2 points. So then there's the other one to furthermore prove my point that it still has symmetry even though when you change the origin or its axes, that I did it to the other equation too, the one that I made up as well. And in the same way, I changed the x values, and then in the same ways, because if you do them the same, if I brought them both down 2, then it would still keep symmetry at the origin, and then y minus 16, because 2 and -16 was the intersection point R from the function that I made up previously in the last problem. Alright, then for the last one, number 6, I had to make a conjecture concerning the real the general cubic polynomial function, that's g of x equals ax cubed plus bx squared plus cx plus d. And my conjecture was just like before in the examples that I gave. Whatever you do to the x values, you have to do the other x values in the equation. What you do to the y values, you have to do the other y values. And every time you make a translation, it will still be symmetric if you keep your values the same as you were translating them like along your polynomial function. Because the parent function of x cubed is also symmetric over the y-axis and the x-axis if it's flipped and altered. So then in the end, you realize that it's symmetric if you keep the x values constant like throughout the equation. So if you're moving one part of the x values down 2, you have to move the other one down 2 as well. You move this one like to the right one, this one has to be to the right one as well, so you can keep the perfect like symmetry within the cubic function. And that's my Math 8 project.